Hello, this week we are going to discuss probabilistic algorithm. And before we start, I thought it's a good idea if we review basic probability theory. And I'm a bit biased here because I did probability in high school, and when I started uni, I also had a few subjects on it. So I'm a bit worried that what I'm going to go through is too easy for you. But as I understand it, as a computing student, you probably didn't have as much exposure to probability as I did. So I want to start with the basics, right? And this will be super boring if you're already okay with the topic. And so I don't know. Let me know what you think. If you're already good with probability, then just skim through this lecture and go back to it if you think you're missing something. We're going to be doing two topics related to probability. One is probabilistic analysis. So that's when you use probability theory to analyze the average case running time of an algorithm. And the second one is on randomized algorithms, or people call this probabilistic algorithms. So that is when you add elements of randomness to an algorithm. And this will sound strange for now, but the whole point is to make you aware of these things. So we're going to go through these topics in the next lectures. But for now, let's just start with some basic concepts in probability theory. Which means there's going to be quite a few definitions that you have to go through, but you have probably heard of all of them before. So first, let's talk about events and sample space. In probability theory, you want to know the probability of an event E happening, and we write PE to denote this. Now, when we talk about probability of one event happening, then that means you have a bunch of events that can happen and just want to know the probability of one specific event happening. For example, if you flip a coin, you can either get a head or a tail. So right away, I'm just going to say that head here is just the chance of, well, it signifies the event that a coin comes up head, and tail signifies the event that a coin comes up tail. Now, the set of all events that can happen is what we call the sample space. So in our case here, there are two events that can happen. Either you get a head or you get a tail. And so the sample space here, S, is just head, tail. So just bear in mind that head, tail here, again, is just a shorthand notation to say the event, the coin comes up head or the coin comes up tail. And the probability of each event happening is 1/2 because there are only two events, and let's just say they're equally likely for now, so the coin is balanced. And we're going to ignore the case that the coin lands on its side, which can happen, but it's super unlikely, so ignoring that. So yeah, that's events and sample space. Now, I can make this slightly more complicated. If you're flipping two coins, then you actually have 4 events. So I'm just going to write HH to signify that you come up with head twice. Or I can do, or you can get HT or TH, like head and tail, or tail and then head, or TT. And the probability of each event happening is 1 in 4. Because, well, you have 4 events here, and let's say they're all equally likely to happen, so it's 1 in 4. But with your definition of the events, if you don't differentiate between the first coin and the second coin, then HT and TH are the same thing. So you can also say that sample space S only has HH, HT, and TT, and the probability of HT is 1/2. Because there are two cases where you have a head and a tail, right? Either you get a head first and then followed by a tail, or you get a tail first followed by a head. So my point here is be careful when you're defining your event and sample space. Because as before, if I say that HT is the event that one coin comes up head and the other one comes up tail, I don't care which coin comes up head, I don't care which one comes up tail. The probability of that happening is 1/2. But if I say that HT is the event that the first coin comes up head and the second coin comes up tail, well, I care about the order. So this is the different event, and the probability of this one is just 1 over 4. So be careful with subtleties like this when you handle problems related to probabilities. Always make sure that you're clear on what the sample space is. Now, you can also work out the probabilities using the probabilities of single coin flip, so PH and PT here. You can do this if the events are independent and mutually exclusive. But this is what we're gonna do in this unit anyway, so you can definitely do this. You can do something like PHT is PH times PT plus PT times PH. But that's the definition of the first event, whereas this one is the definition of the second event. So again, be careful with your definitions, but we're gonna keep it simple in this unit. This does get tricky in real life because you have probabilities of an event A happening that can change depending on whether or not another event B already happened. And you have things like Bayes' theorem, if you heard about it. But yeah, again, we ignore all that. We're just gonna be doing simple stuff. A bit more formal now. We're going to call P a probability distribution. And you can think of P as a function that maps the events in the sample space to a real number. And it has to follow this rule, like the probability of an event must be between 0 and 1. Right? You can't have probability of 2.0. Right? Probability is always between 0 and 1, like 1/2, 3/4, 0.25, whatever. Okay, and furthermore, we are going to limit our discussion to discrete probability distribution. So there's a finite number of events, and we're also going to assume that each event has the same probability of happening, and that is what we call a uniform distribution. So here I say that it's not the probability of an event happening, but instead I'll say the probability of an elementary event happening. So what are elementary events compared to what event we said before? Well, elementary events are mutually exclusive. That is, if event 1 happens, then event 2 can't happen at the same time as well. So the example that we saw before, those are elementary events, because if you flip a coin, either you get a head or you get a tail. But these events down here, they're not elementary events because, well, as you can see, if there are 2 or more tails, that means there are 1 or more tails, also means there are 0 or more tails. So if E3 occurs, that means E1 also occurred, right? And you can see this from the probabilities. The probability that there are 0 or more tails is actually 1, because you're guaranteed to have at least 0 tails if you flip 2 coins. The probability of them being 2 or more tails is just 1/4, because you have to come up tails in both. But the probability of there being 1 or more is 3/4. So if you add up all the probabilities, you'll get 2, which is, well, that means there's an overlap. We're going to assume that every elementary event is independent. So that means if you have n events, they all have probability of 1 over n. If you add them all up, you will get 1. Okay, so well, that's just a rule in probability. If you add up all the probabilities of every event happening, then you're just gonna get 1. Okay, so another consequence of that is, well, as we saw before, the probability of event 1 and event 2 happening is just the probabilities of those events being multiplied together. So as before, you should see probability of a head happening is 1/2, the probability of tail happening is 1/2. So the probability of you getting the head and then getting a tail is just 1/2 times 1/2, but if you care about the order. Now, you don't need to specify that an event is elementary or not. It's not like I'm going to ask you well, I'm not going to ask you about basic probability anyway. But just make sure that you understand, again, the difference between elementary events and non-elementary events. Be careful when there's an overlap between two or more events. That's all I'm trying to say here. Okay. Next one. We're moving on to random variables. So sometimes you need to have a nice way to write probabilities. So the example I have here is, let's say you're rolling a dice, and you can write P1, P2, P3 to tell to say that I got a 1, I got a 2, or I got a 3, and so on. Yeah, right. So you got P1, 2, 3, 4, 5, 6. Another way to do this is to use something we call a random variable. And normally we use X to denote a random variable. So we define that X is the number that shows up on the dice. Now, X is a variable. The value is random because it can be 1, it can be 2, it can be 3, right? 4, 5, 6. And most of the time, well, at least in this unit, we just kind of say that X is going to take a numerical value. And the way we use it is, instead of saying P1, P2, P3, we say Px equal to 1 is 1 over 6. Px equal to 2 is 1 over 6, and so on, right? So we don't just say P1, P2, P3. We say Px equal to 1. But that can change in a bit. Like, just stay tuned. So why do we bother doing this? Because now you can write the probability of some other events in a better way. You can say, what is the probability that X, the value of the dice, is less than 3 or less than or equal to 3, right? You can say, this is 1 over 2. See, because we define X to be the value of the dice, we can say things like P of X less than or equal to 3, because we know what X is. If we didn't use a random variable, you would have to write the actual event in words, something like P brackets, the result of the dice roll being less than 3. So it's just a lot more succinct to be able to say X, to be able to define X to be something and then use X in inequality, like what we're doing here. Now, this will lead to something we call probability density functions, but that's not something we're going to be discussing in this unit, so I'm going to stay away from that. You can define X to be something else, like for example, let's say that we are actually rolling 2 dice, then we can say that X is the sum of the values shown on the dice. Now, what is the probability that X is equal to 3? Well, if you have 3, then either you have 1 and 2 or 2 and 1, so that's only 2 out of 36, that's 1 over 18. I'll let you check yourself if this is correct or not. I hope it is correct. What's the probability of X equal to 6? But see how I can define X to be whatever I want? And I can write the probability a lot more like succinctly. So here's an example, like if X is the maximum of the 2 values shown on the dice. And again, I'll let you check this on your own. Pretty sure this is correct. So the probability of, if you roll 2 dice, the probability of the highest one is 6, is 11 out of 36, because you got 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, and then you got the opposite, so 6, 5, 6, 4, 6, 3, 6, 2, 6, 1, and then you have 6, 6. So that's 11 events out of 36 possible ones, so yeah, it should be 11 out of 36. Okay, so this is why we're using random variables. Now, in practice, you don't have to write Px equal to X, like, well, this is an actual value. You don't have to write P X equal to 1. You can just write P1. All right, so that's kind of clash with how we did stuff before we used random variables, but that's okay. If I see you write P1, P2, whatever, if you define X properly, then I just assume that the constant, this P1 here, is the value of X. I guess the difference with what we did before is that when we define P1, P2, P3, so on, right? That's like we're actually defining 6 events. like P1, P2, like 1, 2, 3, 4, 5, 6. These are the events that the value is 1, 2, 3, 4, 5, 6. But now we're kind of only defining one event, as in the Px is the probability that the value is x. So yeah, like most of the time when you see things like P1, P2, that actually means like Px, where x is a random variable. That's just how probability theory work. Okay. Finally, I think this is the last one that we have to worry about. Expected values. If you have a random variable x, then this x can take different values with different probabilities. Expected value is like the average value that x can take. For example, if you roll a dice, then the expected value is actually 3.5 because you can get 1, 2, 3, 4, 5, 6 equal chance. So on average, you will get 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21. I think, yeah, 21. You divide it by 6, you get 3.5. So that's the average. And we write EX to denote this expected value. Notice the square brackets. And this is computed using the formula x times bx for every possible value of x. And that's just it. So when you roll the dice, this is how you compute the expected value using that formula, right? You can get 1, that's 1 in 6 chance. You get 2, that's 1 in 6 chance. 3, 1 in 6 chance, and so on. You will get 3.5. Now, let me ask you a question. If you flip a coin, then what is the expected value? Think about that for a second. And that is a trick question because you're not supposed to be able to work it out. Just remember that if you have a random variable x, this normally takes a numerical value. And if you want to find the expected value of x, you have to assign a numerical value to the outcomes. Because if x doesn't take a numerical value, then the question like what is the expected value doesn't make sense. So you can't get the expected value of a coin flip. But if you, let's say you play a game of coin flips, let's see what we have here. If the result is head, you double your money. If the result is tail, you lose half your money. Now you can assign a numerical value for these events now, right? Because if you bet $10, if you win, you get $20. If you lose $5. So the expected value that you gain is going to be 0.5. That's a half chance that it comes out head. Times $10. That's how much you're going to win. Or 0.5 times minus 5, because that's how much you're going to lose. All right? So that is the expected value of one coin flip, $2.5. And that means that you should play this game as much as you can, because you're going to end up with a positive value in the end, because you get 2.5 every time. If it's a fair game, then the expected value is going to be 0. As in long term, you should not win more or lose more. So I think that is it when it comes to definitions. What did we go through? We went through events, sample space, probability distribution, that's what P is, uniform distribution, random variables, and finally expected values. And yeah, you've probably already heard about all this before, and you may think that this is maybe a funny way of describing what they are. Well, if you have seen probability before, you know what they are, and if you don't, you can also easily find references online about all this. I'll show you some references at the end. But really, this is all you need to know for this unit. If you understand all this, that's great. I'm gonna say a few more things though about probabilities, because I want to show you that probability can be counterintuitive, or at least it's easy to get the wrong intuition. So these two are famous examples of people thinking about the wrong thing. You can find more discussion about it here in this link here. The question is simple. If a family has two children and at least one is a girl, what is the probability that both children are girls? So this is just like a coin flip, really. You can replace that with a coin flip. The second question is, a family has 2 children and the eldest one is a girl. What is the probability that both children are girls? So for some reason, a lot of people think the answer in both is the same, and it's actually 1/2, which is wrong. Well, it's true for one of them. But with the first question, if a family has 2 children and at least one is a girl, what's the probability that both are girls? And some people say the answer is 1/2 because, well, you fix the first one. The first one's a girl. So now you only have the other one. So can the other one be a boy or a girl? And they think, well, it's 1 and 2. But the sample space actually has 3 events. So you can have the first child being a girl and the second child being a boy. Or the first child being a boy and the second child being a girl. Right? Because it only says here that at least one is a girl. So it could be the case that first child is a boy, second one is a girl. So you have 3 events, or the last one's being both children being girls. So the chance of this happening is actually just 1 over 3, not 1 over 2. So I don't know if you came up with 1/2 when you first saw the question, but if you do, that's a case of not looking at the sample space properly. Because again, there are 3 events, not just 2. Okay, so that's one example how probability can be counterintuitive. Second one, this one, to be honest, to me this is obvious is 1/2, so I don't know what the problem is. So you have 2 children and the eldest one is a girl. What's the probability that both children are girls? Well, to me, the sample space, well, there's only 2 probabilities, like either both girls or the second one is a boy, because you fix the first one to be a girl. So this one, yeah, the probability is 1/2. I don't know how you can stop this up, but if somehow you have a different guess when you saw this question first time, if somehow you don't think the probability is 1/2, then again, just look at the sample space. There's only 2 possibilities now, and so if they're both equally likely, then you have 1/2 chance. Okay. Another fun topic about probabilities, the Monty Hall problem. This is probably something you've heard about before. So you're in a TV game show and there are 3 doors. Behind one of the doors is a car. So if you pick the right door, if you pick the door with the car, you will win the car. The other 2 doors got nothing behind them. Or we're gonna say that there's a goat behind the door. I don't know why I pick a goat. I just did. After you made a choice, so you pick a door, and then the game show host, who knows which door has a car, the game show host opened one door, and there's a goat behind the door. So you got 2 doors left now, and you get asked the question, do you want to change your door? Do you want to choose the other door, which you did not pick? And majority of people say, it has no difference. If I pick 1 or if I pick 2, well, that's 50-50 chance, right? So who cares? I still have equal chance. This is actually incorrect. And it's always better if you actually change the door that you pick. Why? Well, let's say there are 4 doors. So there are 4 doors, you pick 1. Let's say you pick door number 1. And then 2 doors are revealed and you see 2 goats. Now, are you going to stick with number 1 or are you going to swap to number 2? But even this example, you might still think, well, no, I mean, there's still 50-50 chance, right? There's like 50% chance to sit behind door 1, 50% chance to sit behind door 2. Let's use a bigger example. Let's say there are, I don't know how many doors there are, but let's say there are lots of doors, like 100 doors. You pick 1, you pick door number 1. And then the game show host, the game show host knows which door has the car. So he or she opens every single door except for 1, or except for, 2, I guess, the one that you pick, and let's say door number 2, and ask you the questions. Hey, do you want to swap? Do you want to swap or not? What would you do? at this point. Are you still thinking that there's a 50-50 chance? Hopefully at this point you will swap. As in, if you pick 1 before, you're now going to switch to picking door number 2. Why? Well, I hope you can see it, but it kind of makes sense, right? Because the game show host knows which door doesn't have the car. So he eliminated a lot of stuff for you. Now, here's the thing. Let's say there are 100 doors. And you pick door number 1. When you pick door number 1, you have 1 in 100 chance of that having the car behind it. And there's 99 out of 100 chance, 99% chance that the car is behind all the other doors which you did not take. So 1% chance on this one, 99% chance on all the other ones. So let's just say there are 2 events, only 2 events. One event is the car is behind my door, and the second event is the car is not behind my door. If you add up the probability, you will get 100%. Like 1% chance the car behind my door, and 99% chance the car is not behind my door. So now, well, if all 99 doors are closed, the chance of you picking up the door with the car is also still 1% because you got 1 out of 99. Well, 1 in 100 overall anyway. But if all 98 doors have been opened, then the chance of the car being behind door number 2 is 99%, not 1%. The 1% is behind door number 1. The chance of not being behind door number 1 is 99%. There's only 1 door left. That's your 99% here. So here's a write-up for it. If you did not get that, you can try to read this on your own time again. I kind of break it down a bit slowly here. See, this is what I'm saying here. The 99 doors that you did not choose have 99% chance of having the car. If you remove 1 door, you have 98 doors left. There are still 99% chance. If you remove 2 doors, you still have 99% chance. You remove 98 doors, you still have 99% chance of having the car. You have to be able to say, you have to be able to see what the elementary event is. Okay. So that's obvious with 100 doors. With only 3 doors, the door that you choose have 1 in 3 chance of having the car. The doors that you did not choose have 2 of 3 chance. So if 1 door is opened, right, now you only have 2 doors left. If you stick with the door that you chose, you have 1 in 3 chance. If you swap, you have 2 of the 3 chance. Yeah, so hopefully that makes sense. It's a very nice problem. Just tells you that probabilities can be counterintuitive. It's not always what you think it is. And there's one more here. This is more of a joke, really. But I found this true in real life. I found that humans are very bad at randomizing things. So tell me if this is true or not. If I give you, if I give you numbers between 1 and 10, and I'll tell you, give me 5 random numbers, there's a very high probability that whoever I ask is going to give me 5 distinct numbers. Like, oh, give me a random number, give me 2 random numbers between 1 and 10. No one's going to say 2 and 2. Like, well, very few people are going to say that. Most people can pick 2 different numbers. But in reality, the chance of you picking, like, if I ask you, give me 5 distinct numbers, give me 5 random numbers from 1 to 10, there's a very high chance of a repeat. And humans just don't do that. Humans are bad at randomizing. So that's I like this Dilbert cartoon about it. That's a very nice way of saying that. And yeah, I think that's it really. So just some fun stuff at the end there to hopefully make you interested in probability, because otherwise it's pretty dry. So again, in this unit, we're only doing simple, basic probabilities. Actually, the most common setting here is just, here's an array with n elements. pick a random element, the probability is 1 over n. That's really it. And again, we are doing this very informally. This is not a course on probability. If there are statistics lecturers or like math lecturers looking at how I treat probability, they may get very angry. Or if you're a stat or actual student, you may not like it how I did it. There are references like CLRS Appendix C. It's actually very good treatment of probability, and to the level that you need as a computer scientist. You don't need to go nuts on probability. I mean, you have to do a math degree or statistics degree if you want to be good in probabilities. There's also a very nice website here. I'll let you check it out yourself, but it explains probability with lots of little examples and pictures. Pictures are always nice. So yeah, give it a go. Look at it, especially when you have time later on after the semester during your break, because I think it's good to know basic probability. You don't have to go really deep into it, because it can get quite hard. But if you know enough to get around, you will do much better in writing algorithms. I really think so. All right, so that is it for probabilities. And yeah, when we come back, we'll do the two stuff that I said we'll do, probabilistic analysis and randomized algorithms. All right, I'll see you then.